I didn't want to get to this point, but I realized that there were so many mistakes that I had to restart. So here it is. Let's find the homogeneous, solve the homogeneous system. And that is this one right here. With this f of t equals 0, that's the homogeneous system. So to solve that, we're going to have to solve the eigenvalue problem. So we're going to have -1 minus lambda, 5, -1, and 1 minus lambda. And that has to be equal to 0. The vertical lines means that we're going to find the determinant of what's inside. I'm also factoring out a -1, and I get the following. So I multiplied this by this and factored out a negative from both of these terms. So the -1 minus lambda, if I take out a negative, it becomes +1 and positive lambda. And then 1 minus lambda becomes positive lambda, but -1. And I wrote these negatives on the outside so that I can simplify them in a second. And then I subtract 5 times -1. And that is how to find the determinant of a 2 by 2. So the first thing I do is I realize that these cancel out, just the signs. And then this is the difference of squares. So lambda squared minus 1 squared, which is just 1. These negatives cancel. So we really get +5. And all of that is equal to 0. So what do we do at this point? Well, I write it over here. For some reason, it didn't take the whole thing. And now I simplify. So that's lambda squared plus 4 is equal to 0, which means lambda squared is equal to -4. Okay, so I take the square root of both sides, and I get negative plus or minus the plus or minus square root of -4, which I can rewrite as the plus or minus square root of 4 times square root of -1, which is equal to plus or minus 2i. Now I'm just going to look, since I know that I have to do this process with complex eigenvalues only for one of the two, and then the other eigenvector will be the conjugate of the first one I find. So I plug this lambda back in, and I get -1 minus 2i and 5 and -1 and 1 plus, so 1 minus -1, so that's 1 plus 1, which is 2, minus lambda becomes a positive lambda. Well, let me write it down. So that's going to be 1 minus lambda. Nope. See, I made a mistake here. We're just subtracting this. I was looking at the wrong thing. Things weren't making a lot of sense. So I have 1 minus 2i here. And this is our matrix. Then we get k1 and k2 here, the components of our eigenvector, and that has to be equal to the 0 vector. So now, let's check that these two rows are dependent. So if I write 1 plus 2i by taking out a negative, plus 5k2 equals 0, and the bottom is going to be negative k1, so negative k1 plus 1 minus 2i k2 equals 0. Now, can we get to this by multiplying by a single number? Well, I can multiply by 1 over 1 plus 2i. And if I do that, what happens? Well, first of all, let me indicate that I'm multiplying here. What happens if I do that? Well, if I do that, what happens is I get negative 1 plus 2i times 1 plus 1 over 1 plus 2i, so divided by 1 plus 2i, k1, plus 5 over 1 plus 2i, k2, equals 0. I just multiplied the top equation by 1 over 1 plus 2i. So here I get a 1, and so here I get negative k1 plus 5, and I'll leave some space here. You'll see why in a second. 1 plus 2i. Well, let's multiply this by the complex conjugate so that we take this away from the denominator. K2 equals 0. Well, now we have negative k1 plus 1 minus 2i, 5. Difference of squares, 1 minus 4 times I squared. K2 equals 0. So negative k1 plus, well, this becomes, I squared becomes negative 1. So negative 1 times negative 4, that's going to be plus 4. So this becomes a 5, which means this whole thing becomes a 1. And we're just left with 1 minus 2i, k2 equals 0. Is that? And that is this one right here. So far, we're looking good. So far, we're looking good. Now, we can say that 1 minus 2i times k2 equals to k1. So let's say that k2 is equal to 1, then k1 is equal to 1 minus 2i. So our k vector is going to be 1, nope, k1 is 1 minus 2i, k2 is equal to 1. So we can say that the real part is 1, 1, the imaginary part is 2, negative 2, 0, with an I on the outside. So when we mean the real part, this is the real part of the k vector. And the imaginary part, we mean only the coefficient of the imaginary part. This is important. I have stumbled upon this. So now that we have this, you have to remember, well, it's not that you have to, it's a good practice to remember a theorem that makes your solution real. You can do it algebraically, but this is significantly faster. So this theorem says that you can write x1 as e to the alpha t, where alpha is the real part of your eigenvalue, in this case that's 0, times b1, which is this. So let me say, we'll call this b1 and this b2, where b1 is the real part of your eigenvector. So b1 times the cosine of beta times t, where beta is the coefficient without the sign. I stumbled upon that one too. Without the sign in front of I. Sorry, and then you're multiplying all of the whole thing and subtracting b2 times the sine of beta t. And this is your first solution, and your second solution looks similar, but you swap the b1 and b2, and then you have the cosine of bt plus b1 times the sine of bt. Now, I don't like saying just to memorize things, but this one, you can have it in your formula sheet while you take the test. And this is nice to have because it makes things much, much faster. So for our case, we'd have e to the 0t times b1, which we said is 1, 1, times 1, 1, times the cosine. What is the coefficient of the I? It is plus or minus 2, so we're just going to take the 2 without the sign. And then b2 with that negative. Don't make the sign mistake. Negative, and b2 is going to be negative 2, 0. So negative 2, 0, sine of 2t. Now we close this, and then we write x2, e to the 0t, negative 2, 0, cosine of 2t, plus 1, 1, sine of 2t. And so now we can say that our complementary solution is a linear combination of these two solutions, which is, well, this becomes 1 and this becomes 1 because anything to the 0 power becomes 1. So now we just write C1 times 1 cosine of 2t minus negative 2, 0 sine of 2t and plus C2 times negative 2, 0 times the cosine of 2t plus 1 times the sine of 2t. Now, before we move on, what I would like to do is to check whether this is true. And to check whether this is true, you need to find the derivative of this, and you need to plug it back into your homogeneous system. So I'll show you how to do that in MATLAB, and then I'll show you how to do part B. But let's start, sorry, not part B, how to do the particular solution. But let's start first finding the particular solution. There's several methods. The method I'm gonna discuss is undetermined determined coefficients. And this mirrors the method that we use to solve single differential equations. So I look at my f of t, and I notice that it is composed of 1, 0 sine of t and of 0, negative 2 cosine of t. So a good guess for this would be a1, b1 times the sine of t plus a2, b2 times the cosine of t. Because the derivative of this has to be a combination of sines and cosines. So now that we have this, we're going to find the derivative of it. So xp prime, which is going to be a1 b1 cosine of t minus, because a2 and b2 stay the same, but the derivative of the cosine of t is going to be negative sine of t, so I put the negative in front. And then we want to plug it back into our original equation. Now it's not a homogeneous anymore, it has that f of t in there, and see, and match the coefficients to find the values of a1, a2, b1, b2. Sorry, to find the values of how many, yeah, a1, a2, and b1, b2. So let's go over to MATLAB, and I'll show you how to do this. See you there.